So how far between cheese and coffee? Today we're going to be looking at what a hierarchical navigable small world diagram is and how LLMs use them to predict what word is next in a sequence. So the reason that I'm presenting this is because I was looking into some certifications and found this diagram and sort of said, what? What's that? Doesn't make any sense. So I dug into it a bit deeper and I found this. And instead of clearing anything up, that made it worse. Now I've got three things that I don't understand. So to understand the solution, the first thing you need to understand is the problem. So we'll take a step back and look at why do we need this sort of solution? We have four concepts here: red, green, cat, blue. Can anybody tell me which one of them is the odd one out? Why? It's not a colour. Perfect. So we can understand that the rest of the colours, this is an animal, so that's the odd one out. But if you're an LLM and you've just got some words, some ideas, how are you going to know that? Similarly, we've got 5 different objects on the screen. Which two would you say are the most similar this time? Cat and dog we've got. Any others? Orange and cheese. So probably not the t-shirt, but we have different options. And can anybody really say for sure what's more similar, a dog and a cat or an orange and cheese? You've got different concepts there. You've got food, you've got animals, pets. Which one of them is the most important? Why? And then final question, which one of these is most similar to an orange, a dog or a t-shirt? Maybe. It seems like a ridiculous question because it is a ridiculous question. But again, if you're an LLM, you've got thousands of words and you need to figure out which one is next, which one is closest to what I should be doing. So you're going to find nonsense questions like this. So why do we actually need this in the real world? I've used Google as some examples because I think it's something everyone understands. So instead of having to do a keyword match, which would be fairly useless, we can just do semantic search. Because humans aren't predictable, I think the majority of people would say fluffy, but I've searched for fuzzy socks. And then a lot of the results here say fluffy, because the model has understood that's sort of a synonym. It means the same thing. So I'm going to show you the results for this as well. And that makes the quality of your results a lot higher. So I got that guy who played the famous detective. So it's found me the right answer. I did want Sherlock Holmes, and I did want an actor, but it's understood from that guy, actor, and it's broken down famous detective into Sherlock Holmes, but we've also got quite a lot of other famous detectives, so it's also got that concept of ranking. It's understood which one's the most likely famous detective. And then the last example of real world use, that guy who invented the thing that lets people talk from long distances. Hopefully nobody's using Google like that. I would imagine some are. But again, it's understood that thing that lets people talk from long distances is a telephone, and that I wanted an inventor. So that's how we use it in real life. It makes everything a lot more easy to use, and easy to use for humans instead of for machines, because humans are obviously unpredictable. You can't say exactly what format they're going to ask you questions in. Cool. So this is now digging into the maths of, we've got those concepts, but how do we represent them as numbers? Because if I'm a machine, I want everything stored in numbers. What we have is called an embedding. So what an embedding is, you can essentially say it's of type vector, and a vector is just a list of numbers. When we're talking LLMs, those numbers, are all going to be between -1 and 1. And everything in the same position will represent the same thing, which I'll show you a bit later on. Each single number is a dimension. So we've got 5 dimensions in this embedding, so 5 different aspects of this thing. And in this case, this string of numbers is representing the concept of cheese. So it could be a concept, it could be a word, it could be a whole document, an image, it really could be anything. But any data you can represent as a set of numbers. So what I was saying about the same position, we've got 3 different simple embeddings here, 3 different concepts. And everything that's in position 0, we've got taste. So we've got 0.91 is the taste for cheese. It's pretty good. 0.67 is the taste of coffee. Also pretty good. Minus 0.8 is the taste of book. Probably not going to want to eat that. And similarly, you might have smell, validity. When you're using real LLMs, obviously, this is where the sort of black box aspect comes in, where nobody fully understands what each of these dimensions represents. And they might not be something humans really understand as like a single concept. But if it's in the same position, it always represents the same thing if you use the same embeddings model. Okay, so for our example, we're going to use 2 dimensions just because it's easy to visualize. But all of the maths is exactly the same if you've got hundreds or thousands. Never going to have more than that, really, just because of the overhead of computing. But yeah, the maths holds up. This is just so you can see it easily. So we've got a small graph and we're using 2 dimensions. So when we want to know how far apart these things are, we're going to need some sort of quantitative way of knowing that, so an actual number. So you've got various ways you can do that. Cosine is different from the rest in that it uses angles. And if it's close to 1, that's very similar. Close to -1, very different. Whereas the linear ones, everyone understands Euclidean distance, that's just draw a line between 2 points. And you've also got these distances called Manhattan and Chebyshev. So how Manhattan works is that you take every single dimension distance and add them all up. Chebyshev is, again, it looks at single dimension distances, but you just take the longest one. So for our real example, we're going to use the cheese and the coffee. How far between those? So cheese is at 3,4, coffee is at 2,8. So our Euclidean distance is the blue one. We've drawn a straight line, 4.13. Chebyshev is 4 because it's the longest single distance between 1 and 4. Manhattan is 5 because you've added 1, 4. It's the total of all those distances. And the cosine is the angle that it makes with the origin, and that's close to 1, so it means they're very similar. It's a lot of maths. Humans probably don't like doing that much maths, but neither do computers really. They're very good at it, but if we want to be able to efficiently search, we need to be able to do as little maths as possible. So you can imagine that with an LLM, if you need to, every single time you need to produce a new word, and you need to cross-reference every single word in the English language to see what's next, that's probably not going to work. That's just not going to return anything efficiently. So how do we search efficiently through those words to find out what's next? That's why we need those hierarchical navigable small worlds. And as an aside to that, the acronym is HSNW, which is no faster to say. It is just an unwieldy conglomeration of words. There's no good way of saying it. So back to this diagram, what this represents. On the left, you have your hierarchical navigable small world. On the bottom, you've got your navigable small world with no hierarchy. And the top is called a probability skip list. So we're going to start by just looking at the navigable small world. So navigable small world, first thing we need is a world. There's our world. It's a 2-dimensional world. Small world. So the reason that it's got small in the title is that it doesn't work very efficiently with a large number of data points. So it's a limitation. We're not going to be able to use this out of the box for an LLM because there's thousands of points. But for our example, 5 points, perfect. That's a small world. It's a navigable small world. What does that mean? It means that from each of the points, you have defined paths that you can get from one point to another point. So these are the connections. And we say that we've got, if the coffee's our starting node, we've got friend nodes. So the cheese and the t-shirt are friends of the coffee. And you've got these defined paths for every node on your graph. So we've got all these links here. So that is essentially the same thing as this diagram. But what we need to figure out is what's closest. So at the bottom, I've got a home symbol. Every time you start a search, you've got a defined start point, and you'll always start there. In this case, we've got a target at the top, which is a cross, and we need to figure out which one of these things is closest to that cross. And the way this works is a phrase I quite like. It greedily traverses the graph. So it means at each stage, it looks at those defined paths and said, okay, which one of those is closest to the target? So we're starting at the blue house at the bottom, and it's saying, okay, is the coffee or the t-shirt closer? I think the coffee is closer to the X. Okay, wrote the coffee. So now we need to decide cheese or t-shirt. Cheese. And then from the cheese, bread, book, bread. And from the bread then, is the book closer? No, we're already at the closest one. So we can say that's our endpoint. The bread is the closest to our target. So that's that one. It's small in that it only takes a few nodes, so it's not going to work for an LLM, but it is an efficient way of searching data. Because if we go back to this, we can see that we never really even had to consider the t-shirt or the book. We never even got to those, we just skipped past them. So now we also have this idea. So we need a way of doing this efficiently for a lot of data points. So we're going to need to combine it with something else. That's where this probability skip list comes in. So if anybody's ever used binary search, it's not a dissimilar concept. Works slightly differently, but that's the same thing. So the limitation here is that it only works with one dimension. So again, we can't use this out of the box for an LLM because we're working with a lot of dimensions. What it does is it finds one item in a list that you've ordered. So we've got an ordered list of numbers and we need to find 11. So what you do, your first step is randomly split that list out into different layers. So your lowest layer is going to have all of the data. Your highest layer is going to have the least data with the furthest distance apart. And that means that you can make decisions quickly. So for the first layer, all I need to know is 11 higher or lower than 5? Higher, one decision, and you can just skip straight down and say, right, I'm never going to have to consider 3. So you take sort of small chunks of it. So going back to that original one. So we have the same thing but represented as a diagram. So we're going to start at the top and say we're looking for 11. So the first piece of data I'm going to hit is 5. We say, okay, 11's higher than 5. Keep going. End of the list. We've missed it. So we'll go back to 5 and go down a layer. So this time we don't need to worry about 3. We know that 11 is higher than 5. So we're starting at 5 on the second layer. Going up, and the next thing we find is 19. Okay, too high. We'll go back down a layer. So now we're on layer 1, 5, 11. Perfect, we found it. We don't need to worry about layer 0. Skipped. So of this list of numbers, you've only actually had to look at 3 of the numbers in the list to find the one you needed. So it's allowed you to skip out a lot of the searching. That's where this comes in for efficiency. So we've got the probability skip list, which efficiently searches, but it only works in one dimension. We've got the small world diagram, which is very good at finding the closest distance, but it only works for a small amount of data points. So we need some way of combining those. We need both of those functionalities. That's what a hierarchical navigable small world is. So you can see from that diagram, it's just a small world diagram stacked on top of each other. So it's a set of them. So you've done the same thing as you had for the probability skip list. You split out your data and said, my bottom layer is going to have all of the data. My next layer up is going to have some of the data. And as you go up, I'm just going to have less and less data. So for our example, we're going to say layer 1. At the bottom, we know we've got 5 pieces of data. But at the top, we're going to start with 2 pieces of data. So from our home, we can just make one decision and say, okay, book closer to our target than coffee. Let's drop down a layer. And this time we can start from book. Okay, we've added some data. We've got the bread. And you can see it's also slightly zoomed in. So every time you go down a layer, you're not considering the entire data set. You're just considering the sort of target area between target and where you're starting. So it allows you to skip out a lot of that data searching. So here again, we've just got the decision, should I stay at book? Should I go to bread? Bread's closer, let's go to bread. Final layer. Okay, we've got cheese now, but that's further away, so we'll stick at bread. This is our closest one to the target. So that essentially is how it all works. So probability skip list, efficient searching but one dimension, navigable small worlds, very good for close together, but only for small pieces of data. Hierarchical navigable small world allows you to use all the data and split it out into different layers and efficiently search. So what we would use for LLMs. So This is my final real life application of how we might use it. So Spotify uses this for its searches. What I've searched for is I've lost my keys and my bus was late. If I was doing this with just keyword search, it would return. I don't have any songs that are called that. But because I've done semantic search, it's given me a song called Just One of Those Days. Also got keys, panic attack. So that's how we use it. So feel free to send me any of your searches or, ask questions there. But yeah, that's essentially it. Any questions? Mhm. Yes, so the question was, in the context of the LLMs, when you're skipping down the levels, would there be a point where you're close enough to the target that you would stop searching the lower levels and just say that's close enough? I think, I'm not 100% sure, but I'm pretty sure the answer to that is no. You would always go through every level, just check, is there anything further away from this? Yes.
LLM?
Large language model, so ChatGPT, OpenAI. That's what is an LLM.
Skip list, so you just randomly pick distribution data of the different layers. Is there any way you can inform that difference being random to make it coefficients or random escalating?
So the question there was, when you're randomly spitting out your probability skip list, is there kind of an efficient way of doing that or a better way of doing that, or is random the correct way? I don't know enough about maths really to give you a proper answer for that. But as far as I've done it, whenever it's done, it's always done randomly. You just have some sort of algorithm behind it which will randomly split out your data.
That's still on in a 2D world, right?
Yes, so a probability skip list is always one-dimensional.
I mean the map, the final one combined.
So the final map was something that I was representing with two dimensions. But when you're using LLMs, it's usually hundreds of dimensions, but the maths all still holds. You just can't represent it nicely in a diagram.
All the properties of cheese at once, essentially.
Yeah, so it's working in a multi-dimensional space and figuring out, using those Chebyshev or cosine distances, what is the distance between these.
Do you know if like vector databases use some kind of thing?
Yes, so do vector databases use the same thing? Yes, they do. This is how they work as well.
Using this with AWS Open Search vector database, and it said HNSW. Didn't know what that meant until Daisy's got it. That's some kind of algorithm is using to be closest match. I'll let that detail just be handled by them.
What does HNSW stand for?
Hierarchical Navigable Small World. No questions on the chat here. Any more in the room?
You said that you have how do you define a small world? Like, do you use a clustering? When you said at the start that you can't use small worlds for LLMs because there's LLMs too big, lots too much data.
Yeah, so the question there is, what defines small in a small world? I think it's fair. So you could put all of your data in one of those, it just wouldn't work very well. So it's more a case of performance versus how much you can put in one layer. It's just that because of that graph structure, it uses a lot of memory when you're doing it. So it's just very low performance if you use too much data. So I guess the answer would be, based on your use case, you would figure out a suitable boundary for you as to how much data is in each layer.
How is this like inserted? I don't know, but like inserted into an LLM itself, because obviously the things go around, right? You can't just have this small world and there's your LLM.
That'll be then part that.
Yeah, so the question was, how does this integrate with LLMs? How does it kind of transform from this diagram into actually being able to use it? And it's mostly used for, I think as Matt said, the vector searching and being able to find either content retrieval, where it's looking for some sort of document to support it. So if you say to the LLM, you know, search on Google for this, it's finding the most relevant document or in your own database. That's where it's majority used rather than the LLM itself.
So it's more like search.
It's essentially a way of searching.
You mentioned that there's just ridiculous number of dimensions for things that we as humans might not necessarily recognize as a concept, or how do we know? I'm assuming because we don't recognize them as a concept, that they're being automatically generated by something and the training is happening. How do we know that the dimensions that we're generating are actually useful for us to index on?
So the question there was, when embeddings models generate all of these dimensions, how do we know that those dimensions are actually anything useful or accurate? The answer really is we don't. You're working with AI, it's you chuck in some data and it spits something out, and you have to evaluate that with kind of complex LLM testing methods. So you can use LLM as a judge, you can use, you know, you're very unlikely to be able to look at a set of data and say, I think this embedding means this. But yeah, you don't really. It's just a case of iteration and testing to see, is what I've got fit for purpose, rather than testing the actual specific embeddings that are there.
I want to do something where you look at when a decision was made, which was the most influential dimension, and if it's a poor decision, you could feed that backwards.
Yeah, it's an interesting concept, being able to look at what is the most influential dimension when a decision is made based on these sort of searches. I'm not sure about the testing frameworks that exist, but I don't think you'd be able to break it down to that level of granularity, just because it's, you know, kind of complex algorithms on top of other complex algorithms. It would be very hard to break it down to that level.
The training.
Yeah.
When you actually use this query.
Yeah.
Yeah. Definitely all of this is iteration, as Chris has just said, in the testing stage, and when you're training that model.
It's quite usual. So they're just passing those data, so students like teaching, so I'm willing to go.
Yeah, so this in itself is the diagram is not an AI, so you don't train the method, but it's a tool that AI can use for searching.
Where do we get all the values to build them up?
So those will come from an embeddings model. So your embeddings is the concept broken down into a string of numbers, and you have specific AI models that you will pass in a piece of data to, and it will just spit out those numbers. So that would be training or getting off the shelf the model. Yes.
Yeah. An embedding from any particular model wouldn't necessarily be compatible with an embedding from a different model.
Yeah. So as I was talking earlier about how the first position will always mean the same thing if you get it from the same embeddings model, but that isn't true if you pass it between different embeddings models. Those will mean completely different things.
So there's a thing recently where, like, I know 1,000 records from an API, I didn't get front ended memory, and it just did like a fuzzy match on like, just found, does this text contain this string? So do you think you could possibly create a local semantic search in like Java, such as it would be that means, you know, don't use my open search, which costs an absolute fortune. If you just do it locally.
Yeah, I think doing it locally sounds like it would be possible, but as I said, it might be very expensive. or it might be more effective just to see if there's some kind of cheap model that you can use to do that off the shelf.
It is to maintain and query your own methods. That's not possible for a small application.
Yeah, it does. How expensive it is to query and maintain your own vector database depends a lot on your model. It's going to be minimal in comparison to if you're training your own model. The actual storage and querying that database is going to be fairly low cost. I think there's a lot of databases that do. I've been using Mongo a lot recently. I know they have a vector database. I think most commercial systems that provide databases will provide some kind of vector database at fairly low cost.
Registered or vector, and you can get embedding models based on that vector. So you can do it really cheap, but you can do it all out.
It's interesting.
I'm advised using something existing rather than trying to create your own. Probably optimised and. Any more questions? No, thank you very much, Daisy.
Thank you.